So we check for a proof that the work done by gravity is conservative. Well, we'll let dy be downward, and we take the integral of force of gravity dotted into dr around a loop. Whatever dr is, dr could be dy j hat plus dx I hat plus dz k hat. But because f is simply equal to minus mg j hat, f dot dr is simply mg dy. Okay, if we want, we can either define dy to be down so that these are the same direction, or I could put a minus sign here. So I integrate that, I just get mgy from y initial to the same y initial, because it's a closed loop and comes back where it started, cancels out to 0. Okay, so gravity is clearly a conservative force. How about a spring force? Well, the force, f of x, is equal to negative kx. The work is equal to the integral of negative kx dx from x1 to x2, and that is negative k x squared over 2 from x1 to x2. If I put in x1 and x2 as the same value, I just get negative 1/2 kx x2 squared minus negative 1/2 k same x2 squared is 0. So yes, the work done by a spring is also independent of path, or around a closed loop, it's 0. So yep, a spring force is also conservative. But let's look instead at friction. Friction depends on the path you take. If I go along here, the work done by friction is just the force times the little distance. But if I go along the long, tortuous path, along every bit of it, friction is against the displacement, and so the work is equal to the force not times the displacement, but times the total distance. That means that this will depend on the path. If it's a long distance path, I'll have a lot of work. If it's a short distance path, I'll have very little work. So friction is non-conservative. If we compare to the closed loop version, if I just have an object sit there and stay there, no work is done against friction, or no work is done by friction. Whereas if I go around a crazy tortuous loop like this, a lot of work is done by friction. Friction is therefore non-conservative, doesn't store up its work.